Hopefully homecoming's like a lot of fun for you. I'm in sunny California, but don't feel bad for me. Anyhow, let's take a look at today's lesson. So today's lesson, really what we're going to do is we're going to use quadratic models, or x squared equations to model real life problems. So what we're going to do is quadratic models to illustrate and solve, probably quadratic problems. Quadratic problems. Story problems. Woohoo! Story problems. Don't you love story problems? It's okay. These aren't that bad. Okay, let's take a look at example 1. So if I look at example 1, I've got a t squared. So if you throw a ball up in the air, goes straight up, comes down, we're throwing it straight up, it comes down. Over time, its height goes up. So the graph is going to look something like this. You throw it up, but over time, time's going to click 1, 2, 3 seconds. It's going to go up and come down. So that's not the path we're throwing it straight up, down, but this is the height over time. So you get h of t, the height of the ball over time. So find the maximum height. Well, the maximum height looks like the vertex, right? So I'm going to use that little formula I showed you yesterday, and that's going to be that x equals negative b over 2a. Alright, in this case it's t, so we'll have t for time is equal to the negative b, which is my negative 48, over 2 times my a, which is my negative 16. Okay, negative b over 2a. If I put that in my calculator to figure out what that is, I think it's 1.5, but we'll double check 48 divided by 32, and I get, 1.5. That's a time. That's 1.5 seconds that it takes for it to go to its highest height. Now, what's that height? Well, we just have to plug this in. Just take 1.5 and plug it in for t. We're going to get the height. So we're going to go h of 1.5, because we're going to plug in the 1.5 in for the equation to get its height, equals negative 16 times 1.5 squared plus 48 times 1.5 plus 6. Alright, I'm going to use my calculator to get the answer. Negative 16 parentheses 1.5 squared plus 48 times 1.5 plus 6, and I get 42. Now this is going to be in feet. It has to be feet because it's 16. I didn't say feet, but it is feet. Okay, so it's 42 feet. Okay, so what we have is this. It took 1.5 seconds for it to be at its maximum height of 42 feet. Okay, next, find the time when it hits the ground. Well, when it hits the ground, the height is 0. So set it equal to 0. We're looking for this spot right there. So set it equal to 0. 0 equals negative 16 t squared plus 48t plus 6. Alright, it won't factor. So yesterday, what we did was we said, okay, if it doesn't factor, let's graph it and find the zeros. So I'm going to go ahead and go to y equals clear. Now I got to use the x variable, so don't worry about the t. It's going to come in terms of x. Negative 16 x squared plus 48x plus 6. We know x represents time. Window. Alright. It's not going to be in the air very long, so I'm going to make sure maybe -1 to probably 5 seconds. Its height, I do know the height went to 42 feet, so my y max I'm going to change to about 50. Okay, so I'm going to change my window to match the problem. 5 seconds for the x max and 50 feet for the y max. Let's graph it. Okay, there it goes up and down. Now this part of the graph doesn't exist. So we want when it hits ground. That's my 0 there. So again, yesterday we talked about finding the 0. We're going to use our calculate R0. So then we'll use our blue button. We'll go second calculate. 0. Now left bound. Left bound is above it because it is on the left hand side. So back and forth arrows, bring it down till it's right above it. And that is left of it. Okay, I know you're thinking, okay, it's above it, but it is to the left of it. Enter. Just below it is to the right bound. Enter, guess, there it is. So about 3.12 seconds. 3.12 is the time, all right, when it hits the ground. Domain and range. Well, this is a really good question. The domain is normally our x values, right? But the problem is that this problem has nothing to do with x's, it has to do with time. So the domain really has to do with time. Well, let's think about it. It's the time that the ball is in the air. So the ball is in the air from 0 to when it hits the ground at 3.12 seconds. That's my domain. The range. Now the range is normally my y values, but this problem doesn't have anything to do with y's. It has to do with height. So its very minimum height obviously is 0 when it hits the ground, and its top height is where it's at its max at 42. Okay, that's my range. That's in terms of feet. All right, let's make a real easy sketch of this. Let's go ahead and graph it. All right, I'm going to go like this. And this. I'm going to go time down here. 1, 2, 3, 4, and that's in terms of seconds. I know I've got to get all the way up to 42, so I'll go by 10. So I'll go 10, 20, 30, 40, and that's height in feet. All right, we're looking good. All right. Well, from the equation, let's put it down real quick, and I'll bring it back up. From the equation, I know it has to start at 6 feet, okay, just because of the plus 6. So I'm going to put a point at the start, which is about 6 feet, right about there. Okay, that's pretty much a guesstimate. And then I know that it's got its maximum height at 1.5 and 42. So I'll put a point there at 1.5, comma 42. And I know it hits the graph at 3.1 seconds. About there. All I'm going to do is just go ahead and graph it in. Up, and it comes. It's there. Alright? Pretty easy. Now again, this is not the path of the ball. The ball is thrown straight up, straight down. But this is the time it takes for it to go straight up and straight down. That's why it looks like this. Little physics. Turn the page. Alright. Example number 2. Alright, we've got farmer wishes to create a rectangular field using 100 meters of fencing and the sides of a barn for one side. So first of all, let's draw a picture. Okay, here's my barn. And he's going to make a rectangle, right? So it's going to be a rectangular field, so it's going to look something like this. Now if it's a rectangle, these two sides have to be equal. Now, there are lots and lots and lots of ways to make this barn. Or not the barn, I'm sorry, lots and lots of ways to make the field. You can make it really skinny and long. You can make it look more squarish. You can make this be super long this way. So there's so many ways to make this field, but we want to find the best way. So let's start off with this. Let's make this side x, and of course this side's also x because it's a rectangle. These two sides are equal. Now, I've got 100 meters of fencing. So what I use here and here would be used up, and what's left over we would take away from the 100 meters. So if I used x and x here, what would be left for the length would be 100 minus 2x, alright? Think about it this way. If this is 10 and 10, you'd have 80 left over. If this is 30 and 30, you'd have 40 left over. So whatever you use here and here, what's left over goes here, which is 100 minus the 2x. That is an x. Really bad looking x. Sorry, you guys. Sloppy. Now, find a function to model the area. Well, what do I know about the area of a rectangle? Well, it's going to be length times width. So area is equal to my 100 minus 2x times x, okay? Almost done with this part. So I want a function. So let's put it in function notation. Let's put the area with respect to x. But let's change it. Instead of x, let's call this width. area with respect to the width is equal to 100 minus 2w times w. So I'm going to go back into my problem and just change a couple of things. Should have used an eraser, should have used a pencil. But instead of x, let's change it now to w for width. Width. Oh, good, I can fix that x, can't I? So let's go w for width, w for width, and we'll make this a 2w, okay? So we've got it. We've got a function. Area with respect to the width is equal to 100 minus 2w times w. So what are the dimensions to maximize the area? Okay, so maximize. Okay, so if I simplify this, I've got a of w equals 100w minus a 2w squared. All right, looks like a quadratic. Yesterday, we again learned a way to find the max. We're going to use that negative b over 2a. So we're going to say w is going to equal my negative b over 2a. Remember how we did that? So b is 100 because it's with the w, and a is the negative 2 because it's with the w squared. So let's do this. So w is equal to, let's see, negative b, which is minus 100, over 2 times a, which is 2 times negative 2. Get 100 over 4, which is 25. Okay, so what does that mean? That means w, the width is 25. So let's go back to my picture. So my picture, I'm going to have this side be 25 meters. This side be 25 meters. Only 100 meters left, so that means this length has to be 50 meters. So that's the dimensions to maximize the area, okay? Now remember, there's lots of different ways to make this fence, but this is the very best way, all right? Now what's the domain of this function? Well, you got to think about what's going on. The domain has to do with the x values. In this problem, though, the x values has to do with the width. So the domain has to do with the width. Alright, so if it's the width, if I go back and build this barn, this width has all sorts of possibilities. It could be super, super small. I mean, think about all the ways you could build this barn. One of the ways you could do it is make this width almost 0. Don't make it 0 because then you wouldn't have a rectangle. So the width could be almost 0. So width has to be a little bit bigger than 0. Or everything in between. And then the biggest you can make this width is if you went 50, 50. You'd have a super skinny barn with long, long width. But you could have the width be almost 50. Because if you put all of your width as 50, 50, you'd use it for your whole 100. That is the domain. That's all the possibilities you could have to build this darn fence. Okay, so homework. Don't forget to draw a picture, set up the equation, and solve it. All right, have fun at homecoming.